Right, today I want to talk about using a single integral to find the moment of inertia of a uniform solid object about some axis. Now, a lot of times maybe there's other symmetries we can exploit on the object, so we might want to use an alternate coordinate system, maybe not Cartesian, maybe we can use double integrals. That's maybe a little complicated, so today I'm just going to talk about doing it with a single integral. So a moment of inertia I, that single integral, is r squared dm, where of course this is some length and this is some small mass element. Going from here, this usually depends on the shape, so we're just going to use a couple examples. So the first one I want to use is, let me bring in a shape. It's just a thin rod, looks like that's as thin as we can get, that has some length L. And it's going to rotate, we'll say, around this axis. So right here, so it's basically along an axis, just a line. So we're going to let this linear mass density lambda be the mass of the rod over the length. And it's a lamina, so it's a linear mass density because it's effectively one-dimensional. But this implies that dm is equal to lambda dl. Now, this is useful because this differential dm is also an integral up here, and it's really straightforward. So we can see that if we let L equal R, the moment of inertia for the rod just becomes a definite integral from 0 to L of r squared dm, but dm is lambda dl. But we said L is equal to R, so that's R. And we can pull out the lambda because we said that it's a uniform object, so it just becomes lambda integral 0 to L of r squared dr. So I'll draw an arrow up here. I is then, by the fundamental theorem of calculus, 1/3 lambda L cubed. And this is a fine answer, but we defined lambda as m over L, and we still have it in our expression. So we can say that I is then equal to 1/3 lambda. We said that's m. That's going to be m over L times L cubed. Well, this goes away, this becomes squared. Therefore, this just becomes I equal 1/3 mL squared, which is the moment of inertia of this rod rotating about the little line we drew over here. However, a lot of times we don't want it just through some line measured this way, right? We want to make it go to the center of mass. And so for this we can apply the parallel axis theorem. We know the center of mass is going to be right here down through the middle because it is uniform and symmetric, so it's obviously going to be there. So if I draw a new rod this time, let's say I'll just draw one like this. Pretend this is the same rod, right? Pretend it's still very thin. If this is where I'm rotating it about now, this is still R, or this is still L, but we moved this distance is L over 2, right? Because we moved that. So the parallel axis theorem, let's abbreviate that, PAT, says that I perp is just I center of mass, which I'll just call L bar, plus m d squared, where this is the distance we moved, this is the mass, obviously, this is the moment of inertia at the center of mass, and this is the one parallel. So if we apply this, obviously the parallel one is this 1/3 ml squared. This is the one we want. And then we still have mass, and we moved it L over 2 away. So what we end up getting, if we rearrange this a little bit, I'll try and do it where I have room, we get 1/3 ml squared minus 1/4 ml squared equals I L bar. So this whole thing, it's a bad arrow, I around the center of mass is just 1/12 ml squared, right? Because we just take these, all right, 1/3 of 12, well that's going to be 4/12, that's going to be 3/12, so 3 minus 4 is 1. So that is the center of mass for this rod. Very thin, about its center of mass. Okay, that's the first example. I'm going to do another example, and it's going to be a little bit different. So let's just say we have a disk like this. I'm going to draw it not from above, but let's say the disk looks like this here, and it's got some sort of radius out. Let's say this is the center, the radius will be here, and we'll call that big R. I want to find the moment of inertia of this very thin disk about this axis going through it. So if it's spinning in one way or another, where's the moment of inertia? Okay, so we know that the integral for the moment of inertia, just like before, is integral r squared dm. Alright, well, again, r is just r, but dm we have to define something first. I'm going to let sigma, a cross-sectional mass density, is going to be m over a, which is going to imply that dm, just like before, is the density sigma times dA. Well, if this is a disk, it's going to be circular. We know that a is just pi r squared, and we can differentiate this with respect to r. We get dA equals 2 pi r dr. So this is important. We'll use that again over here. So further, this implies that dm is just sigma times 2 pi r dr. So dm, if we bring everything out the way I like it, this is just 2 pi sigma r dr. Alright? Now we can do the actual integral. We have the integral from 0 to big R, that's the radius. We're integrating like disks like this sort of around it. Is basically what this integral is setting up, sort of like a disk there. Integral 0 to r, we said that we have r squared in the integral. We have dm. We said dm is all of this underlined, 2 pi sigma r dr. Because this is a uniform disk, I'm going to bring out the constants and the mass density again from 0 to r, and this just becomes r cubed dr. So if we integrate this by the fundamental theorem of calculus, this is just 2 pi sigma times 1/4 big R to the 4th, because the 0 contributes nothing. I'm going to simplify this a little bit. Actually, no, I'm just going to bring sigma in. So we defined sigma before as this over here, but because we know that area is this, sigma is just m over 2 pi, just over m over pi r squared is our sigma. So we can sub that in over here. This is just m pi r squared times 1/4 r to the 4th. So this is really convenient because the pi's go away. This goes away, this becomes squared. And we see that the whole thing simplifies to 1/2 mr squared, which is the moment of inertia for a disk rotating about an axis through its center of mass. And this is the center of mass because if it's a uniform object, it's symmetrical, it's going to be right in the middle there. So there's that. So now we have 2. The last example I want to do is of a uniform sphere rotating about an axis through its diameter. So I'm going to add another shape and try and make it as circular as I can. Let me draw some lines through it. So this is showing that this is a sphere, right? We'll say that the center of mass is right in the center of that sphere. Let's say it has a radius again of big R. And so if we find the moment of inertia, it's the same, except this time we have to do a little bit different. So I is still the integral of r squared dm. And for this dm, just like always, I'm going to let the volumetric mass density rho equal the mass of the sphere over the volume, which implies that dm equals rho dv. And so now we need a dv. Well, I know that volume of a sphere is just 4/3 pi r cubed. So if I differentiate this with respect to r, I'm going to get dv equals 12/3, which is 4 pi r squared dr. So now we have a dv. So if we do in our integral, we have to do something, we have to acknowledge an assumption we're making. R squared here, the radius, is not just a radius, because if we're integrating with a bunch of little spheres, that radius changes, but fortunately we know that there are some circles that we can have. So if we think of cross sections, think of a circle. I'm just going to pick a variable x squared plus r squared is equal to big R squared. That's the equation of a circle centered at some origin of some arbitrary coordinate system. Well, we can just solve for R squared. R squared is just big R squared minus x squared, right? And if we let R equal x, dv just becomes 4 pi x squared dx. So now we have things in terms of x. So now we can set up the integral. So we'll just say in terms of some variable of integration x. So this whole thing implies that I is equal to the integral of definite integral from 0 to r, because that's the big radius. Remember, we're using cross sections of this big sphere. We said that r squared is this down here. So this is just big R squared minus x squared, and I'll have to put dv in. How do I move this little box? I can't move that box. Okay. And this whole thing is just times 4 pi x squared. And then we put in a row, so now we have dx. So now we can just simplify the integral as we normally would. I'm going to rewrite it again because there's a box there that I can't move. R squared minus x squared times 4 pi x squared rho dx. Everything is in terms of x, and because it's a uniform sphere, I'm going to take out the 4 pi rho, right? 0 to r of, these are taken out, so this just becomes r squared x squared minus x to the 4th dx, and by the fundamental theorem of calculus, this just becomes r cubed, r to the 5th over 3 minus r to the 5th over 5, which we can simplify. And if we do that, which is just 4 pi rho, this is multiplied by 5 by 3, and that's just 2/15 r to the 5th there. We're not done yet, because remember we defined rho as m over v. So rho, I'll just do another one. Rho, because we know that volume is this, is just 3m, let's rewrite that, 3m over 4 pi r cubed. Now let's sub that in. And we'll see that something really nice happens. This is just 4m over 4 pi r cubed over 2/15 r to the 5th, right? 4 pi goes away, this goes away, this goes squared, and what we end up getting, well, this is 6/15 mr squared, but if we simplify this, all right, just divide by 3, right? 2/5, that's a bit too high. 2/5 mr squared is the final answer that we get, and this is in fact the moment of inertia for a sphere rotating about an axis along its diameter, which I should have drawn. Just pretend this is a straight line, so it's going to rotate about this. And that's the moment of inertia. Importantly, again, this is not a hollow sphere. It turns out if we do similar process, is a little bit different. The moment for a hollow sphere is 3/5 mr squared. Similar process, but it's a little bit different if it's just a hollow shell. But this is for a spherical uniform sphere. So this whole purpose of this video was to explain how you might, how you might find moment of inertia using a single integral, and a lot of times, in fact, I know in introductory physics courses, they only give you this one with a single integral, where a lot of times it's more intuitive to do it with multiple integrals, but, we are where we are, and that's not always accessible. So hopefully this is helpful, and this has been the single integral method for finding moment of inertia of uniform solid objects.